Hi.
Hey, Sean, are you there?
Yeah.
All right. How's your morning going for you?
Pretty good.
Good, good. Tell me about the class. How's that coming along?
So my teacher finished grading and
Mhm.
added the curves, and I got an A in the class. So
Hey,
yeah, I'm really happy.
congratulations.
Thanks.
How you feeling about everything?
Really good, honestly. But I'm struggling a bit with like our new unit, but
Uh-huh.
I think I can do it.
Well, okay. Well, hey, that's exciting news. Thanks for sharing. I know you're pretty ecstatic about all that. Okay. Now, let's just kind of jump right into it here, I guess. So, uh, what are you currently working on in your class?
So right now, let me open this up real quick. We're working on like the fundamental theorem of calculus.
Okay. Is that causing problems for you or?
Kind of. I just like don't know where to start when I'm working on some of these problems.
Okay, I'll tell you what, why don't you come over here and why don't you drop some of your problems over here on the bit paper so I can kind of have a better idea what you're looking at, and we'll go ahead and take it from there. Okay, so these four problems.
Hmm.
Okay, so tell me a little about the integration part of this. Show me what you're doing. Let's just grab number one. I'll push these others to the side here for a second. Let me see what you're doing with it.
I'm not really sure what to do, really.
Okay, so let me make an adjustment. Let's say if I was to remove this piece of it, how would you work the problem? A little challenging, right?
Hmm.
Okay, so let me take the two off. Could you work the problem then?
Something just happened. Sorry about that. I accidentally like opened Excel.
Not a problem.
Um, so wait, what does this like D of t stand for? Is it just
Okay,
the
that's going
derivative of t?
that's going to be your differential. It talks about the variable that you're integrating with respect to. It has to do with distortions of areas and volumes based upon which kind of integration you're looking at. For our purposes here, though, for these kind of integrals, it just says we're integrating in terms of t. So that's the variable of integration. And let me just take it a step back furthermore. Let's see if I just take the endpoints off. Could you solve that problem? Okay, pretty close there. So tell me, what did you do
I don't know
to,
why I put two before there. Yeah,
yeah, how did you go about going from here to here? What was your strategy?
I kind of just like reversed it.
Okay. What if I gave you this problem? How would you work that one then?
Wait, what is that?
That's a script too. Let's make it more like that, I guess.
Yeah, just that, I guess.
Okay. Tell me, what was the rule you used to get here? What did it look like?
Power rule.
Okay.
Oh, wait, no,
So
chain rule. Oops.
so the power rule states we have x to a power and then dx. You're going to take the power, crank it up, and divide by it.
Yeah. So this would be multiplied by t. No, not t3. So then
Well,
I have to make this 9 down here.
okay. Well, not really. So here's kind of the thing. This is a problem that some students do kind of run into. And what they do is they say, well, it looks like this, so it must be that. So we're going to get this out of it. The problem is whenever you use these integration properties, Sean, they are very precise, very particular. If it doesn't say it precisely, you can't use it. So you can't guess it to get it to make it work. What you could do if you wanted to make it work, though, there is a technique and it's known as U substitution. You can trade out the U and say equal to 3t plus 2. And then now you'll have the integration of U to the 1/2. If you note, that's exactly what the power rule says. It says the variable of integration to which you're integrating must be raised to a power. The variable to which you're going to be integrating now is U, no longer t, raised to a power. But here's the other issue is the part of dt in the back. See, dt is not something that's just flippantly out there. There's a meaning behind it. So you would take the derivative of your function here, and we see that dt corresponds to a third of a du. So you solve for du or take it and plug it in. What you're going to get is this. To which then, whenever you integrate, you'll have the 1/3 out front and the u that's going to correspond to, you take the power, you crank it up, and then pull it out front. Look at the reciprocal. Don't forget the plus c. And then inside, you would convert back to the original variable, which was this 3t plus 2. And if you were to take the derivative now, the antiderivative is here. You take the derivative, the antiderivative, and we should get back to this 3t plus 2. Now, we'll talk more about u substitution later on, but in this problem, there is some interesting things going on here. Now, the first thing is we do have the fundamental theorem of calculus at work. And the fundamental theorem of calculus, that's from me integrating some kind of function. And it's customary to use t. You don't have to, but it's customary to use t because if I start putting some endpoints on top which have x, like we have in this problem, it's going to be really confusing because we have x down below. And oftentimes we don't do that. It's got to be a different variable. So it's just real confusing because it looks like the same when it's not. So we just circumvent that. We say, hey, it's just t. And you would get your capital F, your antiderivative, and then you don't forget about your plus c. Now, this is the fundamental theorem of calculus. And then the next thing is we can have, or excuse me, the fundamental theorem of calculus is here. The next thing is you're going to take this and you're going to start plugging things in like that. Okay, so use your antiderivative, fundamental theorem of calculus. Then for the next thing, there's another property out there, and it's known as the chain rule of differentiation. And remember what that stated. You're looking at function compositions like f and g. You're going to take the derivative. You're going to get your f prime, plug in your g, and then g prime. Now, when I have this problem up here, let's take a closer look at it. Let's say for a second, if I was able to find a way to integrate this, and there is a way to integrate it, but it's going to require a more heavy hitting machinery. If I was to integrate 1 to x, I have this t squared plus 1 dt. I'm going to get some kind of antiderivative out of it, to which then I'm going to plug in the endpoints from a to b. Now, in this case, the endpoint, the top one, the upper bound's x, and the lower bound, well, that's going to be value 1. Now, the next thing is I just want to come through here and take that derivative. We'll do it in terms of x. And whenever I take the derivative, we're going to have to do this in a linear fashion. So I'm going to break it up in terms of its pieces. So the first piece is we're going to have the derivative of the function, f of x, and then the derivative of the function evaluated at 1. Now, notice this. When I take the function and I evaluate it at 1, there are no x's here at all. So if there's no x's and things which are changing are x's, what does that mean then about this value?
It's a constant.
And the derivative measures rate of change. So how does a constant change?
It doesn't.
It doesn't. 0. Right here, we're going to have the derivative for f. And it is a composition. It's kind of hard to see, but here's my little f that I would have over here, and my little g is my x value. So I would say capital F derivative, plug in g, then I would calculate the derivative of the x, which is going to be 1. But hold the phone. Remember the relationship between your integrand and your antiderivative. If you take the derivative of your antiderivative, you're back to where you started. So when I look at this problem, it seems really, really confusing and challenging until I realize it's nothing more than the square root of x squared plus 1. Done. Now, this right here, this is what's called the second fundamental theorem of calculus. And the second fundamental theorem of calculus uses the first fundamental theorem of calculus in correlation to the chain rule. Now, a few things to kind of observe real fast. Let me take this, I'm going to change it. And instead of saying x and 1, what I'll do now is I'll say something like 4, and let's say x squared. Okay, so we do the same thing. We find the antiderivative. We're going to plug in. We're going to do the evaluation. There's no x's here still, so that's going to be 0. But here I'll have x squared. And remember, chain rule. It's a function composition. So you'd have x squared and then 2x as well. So what the second fundamental theorem of calculus, what it stipulates is if I have a number down below, let's maybe just call it a, and if I had a function up top, let's just call it g, and I'm going to take the derivative of this integral. And I have my function, we'll say f of t to not get confused with the x. And we're going to have the antiderivative of f, which would be capital F. What we're going to do is we're going to take it and we're going to plug this thing in. And then you're going to have to go ahead and take the derivative. And when you do that, the capital F reverts back down to the lower f, the integrand. But you have the function evaluated at g, then multiplied by g prime. Now, this is the fundamental theorem of calculus, second one, and this is really the first part. This is the part that most people are going to be studying. They're going to present this in class, And truthfully, what happens in a lot of these problems is it just goes from a number to X, and students start plugging it in, and they have really no idea what they're doing. Because as soon as you tweak it and change it to your next cube, they keep doing what they did beforehand, thinking that's what you were supposed to do, while forgetting about the G prime. And in fact, on the AP exam, it wouldn't surprise me at all if they take this problem and they tweak it even more. Instead of saying a number down below, if they have a function down below, like h, you're going to go about it the exact same way for the most part. Now, let's go back up here and review it. Remember what happened? We plugged in the x squared and we got our function to which then we can take the derivative. Then we plugged in our number, but we realized it was just constant to begin with. But what if it wasn't? What if it was 4x instead? I would do exactly the same thing. I would have instead of doing this, I would have f prime 4x and the derivative on the inside. So here's the most generalized form of the second fundamental theorem of calculus that you can use. You're going to say f. You're going to evaluate it at g, then g prime. Subtract it off, f, evaluate it at h, then h prime. Now, by really knowing how this thing works, Sean, how much more sense does it make now?
Pretty good.
Makes a lot more sense. So it's a lot easier to remember. So if you forgot it on the exam, what you have to remember, there's two components, two key ingredients. The first fundamental theorem of calculus and the chain rule. Now, with all that said, let me grab your problems. And a moment ago, you said you weren't for sure how to work these. Can you work them now?
I hope so.
Give it a try. Pause for a second. I want you to take notice of this. You are plugging this in, and what I would like for you to do is kind of get into the habit of just saying G prime, at least for the time being, because when they start tweaking this, it's going to pay off. So we'll do something like we'll say one. But notice that this right here, the H prime,
Mhm.
that's a number. How do numbers change?
They don't.
So the derivative is zero. So over here, you would take everything and plug it in, like for number two, but now you don't want to get it 4/3 because when you plug in the three, how do derivatives change?
Oh,
You get zero. So derivatives don't change for constants. Try number four real fast. Yeah, not bad, huh? It's basically just, for the most part, at least what it seems like, it's just you just plug it into the function, and you go about your business. But it's not really the complete story because G prime. All right, good. Now, take a moment. I want you to see if that makes sense.
Yeah, it does.
Okay, because I'm going to throw a few more your way. Ready? There we go. See if you can assess the situation. Now, here we do have our integral. It's a function, a, and what we're going to do is take its derivative. That's all. That's all we're going to do. Okay, and if you were to do the fundamental theorem of calculus, you would plug in from 0 to x,
Yeah.
then take its derivative over 3.
Oh yeah.
And your answer is going to be just simply x squared. Okay, so let's go back up here again and make sure you have this formula written down. They may not give this to you right away. They might wait a little while if they do give it to you. But if you know this formula, this is going to take care of every single one of these kind of problems. Let me give you a moment to write that down.
Okay, yeah.
Okay, so look at this. You didn't have to go through all this work here, did you?
Mm-mm.
Because we got a nice formula for it. Now, b is real similar to what we did before, but notice how it's the cube root, not the square root. So, Sean, what's the evaluation? And give me just one response. Don't give a derivation. What is it?
So it would be
Okay, let me pause you there because what you're doing is you're still trying to evaluate. And this is not how you're going to evaluate this, anyways. So let's back up. Look at the formula I gave you. Here's the f function. Okay. Now, let me just change this up. Let's just call this b since we're using f in our formula. Here's your integral f of t. What did that formula stipulate when I had a g and I had my h?
oh, okay. I got it.
That's it. That's it.
And this will matter if it's 0.
Yeah, because the derivative would be 0. Now, there's that other piece too. I want to kind of get you in the habit of doing it. You want to say 1 here for a little while. It's just going to revert back down. Because look at C. C is a little different. There's no longer an X on top. So how do you address that situation? That's exactly it. And because this down here is a constant, the next piece has to be 0. Okay, D is a little different. Give that a try. Wow, Sean, you got it.
And then I take, oh wait, no, that's, okay, yeah.
How'd you get so fast?
Just use
Wow.
it for very long.
Yeah, yeah. Okay, let's go backwards a little bit. How about that one? And there it is. You got it. So this is what's called again the second fundamental thermocalculus. Okay, so let me review again how it's constructed. You're going to be looking at your fundamental thermocalculus, and maybe we'll say just T here just for parallelism, but we're going to say your f of b, f of a. Then you connect it up with the chain rule, which stipulates if you look at your function composition, f prime g, and then g prime. Now, let me ask you this question. Let's say if you have a fellow classmate who's really struggling with this, they you show them the formula, but they still want to know why. They still want to know why whenever you look at your function here, let's just say it goes from a, and let's say if you have g of x, they're going to ask you, why is this the case? Do you think you might be able to explain to them?
Is a chain rule?
Mhm. Now, I'm going to go back up here. I want you to take a quick look at the example I gave you. Remember how we went about looking at the second fundamental term of calculus?
Yeah.
Okay, so we used the antiderivative, we used the fundamental term of calculus, then we used the chain rule and all the connections of it. Okay, look at the color coding up here. We have this color, we have the antiderivative, then we did the fundamental term of calculus, then we took the derivative, and then the chain rule. Okay, so if you had to say to your friend why this is the case, what would you say now?
Um, what do you mean by that?
How would you explain why this formula is true?
Because of chain rule, I guess.
Okay. We are going to be taking the chain rule on the function. And just remember this part right here. That's going to be the derivative of the antiderivatives evaluation at G. And the other piece, that's constant.
Okay, yeah.
Okay, good. Now, let me throw you this problem. Okay, here's a graph. And whenever you see graphs, you have to ask yourself, okay, is it a graph of f of x, or is it a graph for f prime? So always got to be a little bit cautious with those. Okay, here's the problem statement. So the graph of f of x is shown, and it has a horizontal tangent line at 3. So right here, it's been marked for us. And x equals 3 and x equals 6. So also right there. What is the value of g prime at 3? Do you think you might be able to figure this problem out now?
So G prime is 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3.
Okay, so if this is G, what's G prime? That's your first objective.
So G is the derivative of F. And then,
Well, you don't want to think it as the derivative. G is the integral of F at these endpoints. So it's a function. So this right here, this is literally the G function. It's just expressed in terms of integration.
oh, should I said that the wrong way around then?
So if that's G, tell me what G prime is,
It's just going to be F
not X,
of T.
not T.
Oh,
Okay, 2X and what else? There you go. And then zero for the last piece.
yeah.
Okay, so that's what G prime is. What you're going to do next is take the X and what's it telling you to do?
Put it
Make it
in three
make it three. Where's f of 6 at?
right there.
And that's a value of.
-1.
So what you get then is very good. Very good. Okay, how you feeling about it? Feel a little better or
Yeah.
okay. Now, did you have an additional problem on this that you're struggling with as well?
Um,
Or
I wanted some help with summation as well.
okay, let's take a look at those. Why don't you go and drop some of your problems out? We'll take a look at them.
It's taking a moment to load. Google Drive's not loading for some reason.
Oh, there we go. All right, talk to me about number three right here. What struggles are you having with this?
Um, uh, like I just don't know where to start with this one.
Okay. Now, usually a good place when you're looking at these is maybe the first graph it out, but to try to get some kind of understanding. So if you're to graph this out, what is this graph?
Um, kind of just like this.
Okay, good. So we're gonna have some kind of line. And it's gonna actually go from 1 to 5, and that's the piece that we're really concerned about. Now, when I'm looking at Riemann sums, we're gonna take these rectangles and we're just gonna chop the region up and we're gonna create these rectangles. I can use a left-hand rule, right-hand rule, midpoint rule. There's different schemes I can use. And if I have the vertex on the left-hand side, it's known as the left-hand rule. Now, what I do here is I calculate the area for a rectangle. Well, Sean, what's the area of a rectangle? How do I calculate those?
Length and height.
How do I calculate the height?
Um, Using the point,
Okay. And what measurement on the point refers to vertical measurement for a height?
the y.
The y. And I get the y by evaluating the function. So here's what I want to do. I want to look at the region from 1 to 5. And we're going to chop this up into many, many different pieces. Now, it's not telling us how many pieces, so we're going to do this a whole bunch of times. In fact, we're going to do it n times. And here's something else that I want to do. I want to chop it up in a way so that each piece is equal length. No, I don't have to do that, but it makes it more manageable and easier to go about it if I do that. So we're going to have n partitions. If I want to calculate the length of each subinterval here, what I do is I take the whole entire length of the interval. That's going to be the b minus a, and I'm going to divide it by the number of partitions. This is sometimes represented by delta x. Now, here's my next question. Let's just say for a second n was going to be a value of 4 for a moment. So I have 5 minus 1 over 4. We're going to have 1. And then we're going to have our other values up here. This value is the a value. And we also can designate this by a subscript on the x called x naught, our initial value. Then I would have my x1, my x2, my x3, and then I have my next one, b, which is going to be my x4. What's the value for x1?
Um,
If you're starting here, what's that value?
3.
Not
Wait.
3. Because if the spread
Oh, yeah, yeah.
is 1, how far did you travel?
1.
So the value is 2. And if I go to the next one right here, what's that value?
3.
And so on and so forth. So if I want to go from my starting value, and then if I want to go to the next one, x1 would be this. And if I want to go 2 steps out, I would go 2 steps out. So, Sean, what would happen if I want to figure what's going to happen at the kth value? What are you seeing?
Um, Plus 1, like
What's the
a plus
pattern?
n
Yeah,
um, delta x.
you got it. Okay, so that's the value that we're going to be using. And like you said a second ago, you look at the function evaluation. So you're going to say f evaluate at x sub k or n, whatever value you want to use. Now, in this particular case, we're going to have x sub k. Our starting value is 1. That's the piece right there. Plus, we're going to have k, and the delta x. In the problem again, they didn't stipulate the number of partitions, but we still know how to calculate that. That's going to be 5 minus 1, and we're just going to have to say n. So we're going to have 4k over n. And if I want to get the height of each one of these rectangles, we have to do the evaluation. So the height, we're going to have f x sub k. We're going to have 2, 1 plus 4k over n plus 1. 8k n, 2 plus 1 more is 3. So here's our height. Okay, see if that makes sense.
Yeah.
Okay, this is the height of the kth rectangle. Then, after I have the height of the kth rectangle, if I want to find the area, what would I do next?
Um, Multiply by
By the width.
yeah.
And that width, that's going to be our delta x. Oh, not that right there. That is the
Oh.
location of the kth x
Oh, yeah.
value. So the width, that's going to be our delta x, which in this case is 5
It's
minus 1 over n, or in other words, we're going to have 4 over n. Now, all this does is it just looks at one rectangle. But how many rectangles do I want to look at?
an
All of them.
infinite amount.
That's exactly right. So I'm going to take the area of one rectangle. I'm going to add it to the area of another rectangle. I'm going to add it to the area of another rectangle, and so on and so forth. So I have the value of k, n's fixed, it's outside of this. And we're just going to keep cranking this thing up, and we're going to do this n times. Now, I can use the left-hand rule or the right-hand rule, and I just got to be a little bit cautious about maybe how I'm setting this up. If I started off at 1 and I end at n, I am talking about the right-hand rule. And let's go back to n equals 4 to see that. So if I'm using the right-hand rule, I'm using these endpoints right there. If I'm talking about the left-hand rule, I'm talking about these endpoints right there. And notice 0, 1, 2, and that's going to be n minus 1. So you can always determine if it's left or right looking at the series based upon what's your upper value and your lower value. Okay. Now, from here, we just really want to start assessing this given series. Now, here's the deal. Well, in order to go about the problem at this stage, I'm going to need some special identities right here. This one, 1 to n, this is going to be a value of n. The next one, this is going to be n plus 1 over 2. And the next one, this is another one that does pop up on a regular basis. This is going to correspond to n plus 1, 2n plus 1 over 6. And the last one, this one pops up as a little more rare, which you're going to be doing in this course, but it's going to be n plus 1 all over 2, and you're going to square it.
Is this going to be on like the AP test without like formulas?
It's good to know the formulas. Um, less you have to look things up, the faster you can go to your calculations. This one back here, that's not going to occur that much. This one, if you were to add 1 to itself 4 times, well, what would you get? You get 4. So we can see that one very quickly. This is the one that's going to pop up quite a bit. And this is no one's going to pop up as well. Now, in terms of using this, you're not really going to see this really on the AP exam. What you're really going to see are a bunch of tables. You're going to be looking at Riemann sums, in which you're going to have to be looking at the spread. And you would say, okay, what actually is that distance? And you say it's not uniform. And when it's not uniform, well, you're going to pull away from these identities. But we'll talk about that as we get to those. Okay, so here's your function again. And do you remember the limit definition of a derivative, how you worked out for a little while and then eventually we pulled away from it? And we got to all those different properties like power rule, quotient, product rule, chain rule. The same thing right here. You're going to do this for a little while and then you're going to stop doing it. This is right here is just telling you where integration comes from. Okay, so you're going to take this and expand out. Then you're going to sum it. You're going to pull it out. Factor everything out except for the stuff that has a K in it. Then you're going to replace these values with their special identities up here. Just like that. Now, that's the next step. So you would calculate the area for each one of these rectangles. You would then take the sum, but it's still not a good approximation because how many do you really need? An infinite amount. So the next step here is you would take the limit as n goes off towards positive infinity. And now we know exactly what we're taking the limit of. Is this piece. So we take this problem, we throw it back to our properties of our limits. We assess the first limit, you are going to get 16, and that's constant, so it is what it is. $28. Wow, that was hard. Okay, let me jump back up here real fast. I'm going to take a look at this problem again. Pull it down here.
Yeah, so real quick,
Mhm.
could I just like use like integrals to like do this? Like,
That's
have
what we're
a
about to do here. So if I integrate from 1 to 5, 2x plus 1, we're going to hit it with the power rule. We're going to take the power, we're going to crank that thing up, and then we're going to put that value down below. So we have our x squared. And then we're going to do the fundamental theorem of calculus. What we're going to get here is 25 plus 5. Then we're going to subtract off 1 squared and then 1. So we have 30 minus 2. And look at that.
huh,
Same thing. By all means, yes. Ishan, this is how you really want to do it. You don't want to do it over here like that.
sadly, my teacher wants me to
I know,
do both
because
ways.
because the question stated write it in terms of Riemann sums. So you're going to have to do this in terms of Riemann sums. Okay, so let's back up here and let's see if we can get a good strategy to go about these problems. Okay, right on your sheet, the first thing is maybe we want to go ahead and just sketch it out so we get a visual as to what this is going to look like. Now, it's not really all that important really in these problems, but it gives you an anchor and it gives you the encouragement boost that you need to keep pushing forward. So you don't get stalled within the problem and you feel like I'm getting stalled on, I can't go any further. So that just gets you something on paper and get your hand moving. That's all that's really going to do. So we'll just make that a rule here for the time being. We'll say we'll sketch out graph. Now, the next thing is we want to figure out what's going on with these x values. And here is the value. This is how you're going to write this out. And notice there is going to be a difference between k and n we have to watch out for. And delta x, that's going to be the length of the interval divided by the number of partitions that you're looking at. Now, the next thing is you're going to have to do an evaluation of your function. You're going to have to figure this out. And after you figure your evaluation out, you're going to multiply it by your delta x. And you're going to expand and simplify the values. After you expand and simplify, you have to make the observation also that we are talking about the kth rectangle. So the next thing is, after you expand and simplify, you're going to be taking the summation, start k off at 1. That's usually going to be the best route for you. Go to n and look at the summation of these. Then, after you look at the summation and you're going to take it and crank it and break it, you're going to use one of the 4 identities, if not more of them. Okay, that's going to be your next step right there. Then, after you do this, the next step, after you apply your identities, is you're going to be taking the limit of your summation. And what this here is in the very end, yeah, that's exactly what the integration is for your definite integral. You can always take the integral real fast to check your work to see if the summation's right. But just make sure that if they say use Riemann sums, you make sure you use Riemann sums. Okay, let me drop this link over here. Do you see over in the screen?
Yeah.
Okay, so the stuff over here on the website, this is really going to be helpful for you. You have your Riemann sums, it talks about the formula for the left rule, for the right rule, and then eventually you're going to get into the midpoint rule. But down below, here's where all these formulas are. So you need to test yourself later on. This one, make sure you do know this one and this one as well. These two come up on a regular basis that it's worth your while to memorize these. And not just in this math class, but other math classes. The other ones back here, the cube comes up in a very rarely, but it does pop up. Anything like x to the 4th to the 5th, those generally don't appear. These are the main 4. X squared comes up on a regular basis too, but not as much as x. They are the k value.
Okay. Yeah.
Okay. Okay. Now, I know it's going to take a little bit of time to really digest this. So make sure you do have these step-by-steps plays on how you're going to approach these problems. Let me see if I can put them a little neater so you can see them all at once. Okay, there you go. You can take a snapshot of that if you like. But make sure you go backwards to the website whenever you forget about the formulas, and that's going to help you remember it. And also, here's a nice little app whenever we were talking about the Riemann sums, remember? We can, remember rectangles, we're just going to fit more and more rectangles below it. And this is going to help out too. So you can check your work when you're looking at Riemann sums for the right and lower and see if it actually is going to be the exact that we have down here.
Okay,
You
yeah.
see it's getting pretty close. Okay. All right. Well, Yushan, how you feeling about the topics here for this morning?
A lot better.
Good, good. Okay, so I think you're doing a fantastic job on the second fundamental thermal calculus. Just don't remember that, or just remember that formula that I did give you. And if you do forget, you can always come back over here and you can look up the fundamental thermal calculus. And it is right in here with the derivations for you to look over. And you do have your flashcards down here, so you can test yourself, see what it was again. And here's the most generalized form. All right. Well, Sean, do you have any more questions you want to talk about for this morning or
No, not really.
okay? Well, Sean, you keep up the good work then. And oh, when's your exam? Next exam.
It's next Monday, so yeah.
So it's coming up on the 5th.
Yeah.
Okay, you feeling ready for it?
I hope so.
Okay. Okay. All right. Well, if you need any help on that, just let me know. And is it going to be over these topics or other topics?
Um, it's gonna be on these ones.
Okay. Well, go ahead then and um, watch this recording again later on so you get an understanding again of this summation formula idea, what we did. I want you to go ahead and work about 2 or 3 more problems just like this. Go here
Mhm.
on your problem set, like for number 4. You're going to do it the exact same way for the most part. Uh, let's just work out a little bit. I want to make sure you're really comprehending this. Okay, so we'll go ahead and skip this the sketching part here, but calculate your x sub k. It's going to be 0. That's the a value. You're going to have k, and then 2 minus 0. Remember, we got to figure out the delta x, b minus a over n. You're going to take that and plug it in. You're going to have 2. You're going to have 2k over n raised to the third power. So you have 8, 16, k to the third over n to the third. Okay, that's the height. Multiplied by delta x. And then look at the sum. Start from 1, go up to n. Pull everything out that does not have a k in it. So we're going to have 32 n to the fourth summation k to the third. Then what you want to do is come back over here, look up your identity. That's going to be the cubed. Drop that in for the summation. Okay, so you're going to have 4 goes in 32 8 times. And then after you do this step, then you have to take the limit. So you're taking the limit of your series as n goes off to positive infinity. And you're looking at your n squared n plus 1 squared into the fourth. And that's going to correspond to the value of 1 in the end. Okay. So watch this recording again later on. Just make sure it's all making sense still. And then if you have some additional problems on this, work those two problems and just keep coming back and forth. Okay. Now, let me stop, see if you have a question about anything.
No, I think I'm good.
Okay. All right, then. Well, you have a great day. Keep up the good work, and I'll see you next time.
Yeah, you too. Thank
All
you.
right. Take care.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.